In this video, we look at equilibrium points in state space models. A state space model is a system of differential equations written as one first-order vector equation, x dot equals f of x. Here, x is the state vector, and f of x tells us how the state changes over time. An equilibrium state is a state where the system can remain constant. If the state stays at xe, then it is not changing. So x dot equals the zero vector. Since the model says x dot equals f of x, the equilibrium condition becomes f of xe equals the zero vector. So the state space rule is set the state derivative vector to zero, then solve for the equilibrium state. The vector x contains the state variables, and xe contains the corresponding equilibrium values. Now let's unpack what the vector equation means. The state derivative vector contains the individual derivatives, x1 dot, x2 dot, up to xn dot. The vector function f of x has matching entries. f1 gives the equation for x1 dot, f2 gives the equation for x2 dot, and this continues for all states. At equilibrium, f of xe equals the zero vector. That means every entry of the vector must be zero at the same time. f1 of xe equals 0, f2 of xe equals 0, and so on. This is the useful state space idea. One compact vector condition represents many scalar conditions that must all be satisfied simultaneously. We can also include inputs in the state space model. In that case, we write the model as x dot equals f of xu. The input may also be a vector, containing input variables u1 up to um. With inputs, equilibrium depends on both the state and the input. At equilibrium, the state is xe, the input is held constant at ue, and the state derivative vector is 0. So the equilibrium condition becomes f of xeue equals the zero vector. This means the equilibrium is a state input pair, xeue. For a linear state space model, the same idea gives the zero vector equals axe plus bue. The state and input must combine so that the state derivative vector is 0. Now we apply the state space equilibrium condition to a simple second order example. Suppose we have q double dot plus cq dot plus k sine q equals u. We choose the state variables x1 equals q and x2 equals q dot. So the first state equation is x1 dot equals x2. Rearranging the original equation gives the second order state equation x2 dot equals minus cx2 minus k sine x1 plus u. Together, these give a two-entry state derivative vector. The first entry is x2, and the second entry is minus cx2 minus k sine x1 plus u. At equilibrium, both entries of the state derivative vector must be 0. The first entry gives x2e equals 0, so the velocity state is 0 at equilibrium. The second entry then gives the input needed to hold the system at the chosen position. Since x2e equals 0, the condition simplifies to ue equals k sine x1e. This shows the main point. At equilibrium, the velocity state must be 0, but the position state does not have to be 0. A non-zero input can hold the system at a non-zero position by balancing the spring terms. To finish, let's summarize why equilibrium points matter in state space models. The equilibrium idea itself has not changed. We are looking for a condition where the state can remain constant. In state space form, that means the full state derivative vector is 0. With inputs, we choose an equilibrium pair, xe and ue. This pair gives us the reference condition for the system. Once we have that reference condition, we can describe nearby behavior using deviations. Delta x equals x minus xe, and delta u equals u minus ue. So, equilibrium points are not just values we solve for. They become the reference points for studying behavior nearby. This is what we will see when we linearize a state space model near an equilibrium pair.